Hello everyone, welcome back to 3120 Advanced Organic Chemistry. JP here. Today we're going to talk about the Kliesen condensation. This is lecture 20 and we're going to divide this up in a few different portions over the next 2 or 3 lectures. So specifically, this is a part of the chapter 26 that's dedicated to acylation at carbon. And this can be found in chapter 26, specifically pages 640 and up. Okay, so as I mentioned, this is going to be broken up into a few different portions. So we have acylation of carbon. We'll talk about some of the challenges in doing this chemistry. And then we'll focus our attention on the Kliesen condensation. We'll look at cross-ester condensations, sort of similar to what we did with Aldol cross condensations. We will look at intramolecular cross-Kliesen condensation. And then finally, we'll look at the acylation of enols under acidic condition. Okay, so what we'll focus on for lecture 20 will be those 2 points up there. Okay, so let's talk a little bit about acylation of carbon and what that means. So let's say we wanted to make this compound here. Let's think of how we can make this compound using an enolate strategy and using an acylating partner as the electrophile. So we're going to look at 2 main ways to make this. One would be, you could imagine you have this portion of the molecule on the left form an enolate here, and then this would react with the acylating partner. So we could call this scenario A. Or you could imagine the other way around. The key carbon-carbon bond could be formed from enolate through carbanion here and reacting at that electrophilic acylation partner. So we can call this scenario B. So let's take a look at how we can construct these using these 2 different strategies. So let's look at number or letter A first. So if we look at letter A, we're going to have our enolate that would look like this, and that's going to react with an acylating partner which will look something like this. And a good acylating partner is going to have a group X here. That's a very good leaving group. So you can imagine that this is now your, well, let's write this down. This is your nucleophile. This is your electrophile. And so if this were to come down, you get the electrons going like this. Form that tetrahedral intermediate, then you form back the carbonyl, displace off your leaving group X, and you'll be left with the desired product there. So that's root A. Let's take a look at root B. Root B will be similar, but we're going to use the other half of the molecule. So your electrophile will actually be on the left, and your enolate will be as shown there. So this will react in a very similar and analogous fashion to root A. And then carbonyl forms, displace off your leaving group X. Both methods will generate your product. Okay, and acylation at carbon, put a little title here, involves adding an acyl group to a particular compound. Good acylating agents that you've used before include things like acyl chlorides. Those are very reactive, and anhydrides, which we've also seen in this course already. So here is an example of an acyl chloride. Here is an example of an anhydride. And this acylation of carbon is a very useful way to generate these kinds of structures, which are two carbonyl groups that are separated by an alpha carbon. So they're very useful compounds for organic chemistry. Very useful way to generate compounds with two carbonyls separated by an alpha carbon. Okay, so it looks pretty straightforward. It looks like we have two different ways we could make this. You can imagine you would probably want to maybe have the better electrophile depending on what the X is, and you could, depending on what the nucleophile is and what the R groups are, synthesize that, right? So you have two different choices. But there are actually a couple problems with acylating at carbon like I've shown you here. So I'm going to outline what some of those problems are and how we can try to overcome it. So problems with acylating at carbon. Okay, we know how to generate enolates for sure, right? We've done that a lot this term so far. If we take our acylating partner and we mix these two together, so it's the same reaction like I've shown you down there, one of the problems is that these are actually just really, really reactive. And while it's better for the carbon to react here, what can inadvertently happen is that you can have the oxygen, the negative oxygen from the enolate actually attack that carbonyl center. Okay, so this is the undesired reaction. And if that were to happen, your electrons will go up. You'll generate a tetrahedral intermediate like this. And then the problem is, once this collapses, the X is your better leaving group. So you're going to generate this compound here, which is an enol ether. And it's definitely not what you're trying to make. And you might be wondering, well, why are we worried about this now with acylating a carbon when we've had similar examples when we looked at the Aldol reaction, for example? Well, let's take a closer look. So recall the Aldol. If we had a similar type of enolate, and if this reacted with let's say an aldehyde, question is, well, why did we not consider this side reaction here, like we're doing up there? Definitely a valid point. If that happens, let's take a look at what this will look like. There's your tetrahedral intermediate. This definitely can form, but what happens is that when you collapse that tetrahedral intermediate, what is your leaving group? The only leaving group you have is this one here, breaking the carbon-oxygen bond. So what this means is that this is entirely reversible. This leads to a non-productive step. So while it did happen, we didn't have to worry about it, because as soon as that happened, it would just go back. But with acylating partners, because X is such a good leaving group, if you get that reaction occurring, X is the better leaving group, and then you're going to generate the undesired enol ether. So for example, if you do this in reality, and if you take a ketone, treat this with LDA at -78, you generate your enolate, and then if you react this with an acylating partner, what you're going to get actually is you'll get your desired product, okay, just like the mechanism that we've shown, but you'll also get the side product too. So you get a mixture of compounds. So this is desired, undesired. Mixture of products. So as a chemist, how would we solve this problem? Because it's such a useful reaction if we can generate these compounds that have two carbonyls separated by an alpha carbon. So one of the problems is that the enolate is actually just so reactive. It's too reactive and it's very hot, right? We talked about strong nucleophiles. It's very reactive, it's hot, and it's going to just react with anything. And the other problem is that our acylating partner, whether it's an acyl chloride or an hydride, is also very, very electrophilic. So you mix those two together and they just react almost spontaneously. So what we need to do is we need to actually bring down the reactivity of both of those substituents in order to generate the actual desired product. So what we can do is, how can we control this, is we can use less reactive specific enol equivalents. Lithium enolates, very reactive. So you've learned already some very good specific enol equivalents that are not as nucleophilic. So these would be things like enamines and silyl enol ethers. Those are very good choices and candidates for this type of reaction. Use less reactive specific enol equivalents enamines or silyl enol ethers with the acylating partner. Okay, so you're taking something that's less reactive with a very reactive substrate, or you do the reverse. You use something like a strong enolate, like a lithium enolate, but you use a less reactive acylating partner. And something like this, I've told you that the best ones are acyl chlorides and anhydrides, but the next best acylating agent in terms of reactivity, this is most reactive, next most reactive. The next one would be something like an ester. Okay, so esters. So we'll call this most reactive, next most reactive, and then we'll call the esters like mild reactivity. Okay, it's good enough, but it's not super hot where it's just going to react, spontaneously and in a very quick and uncontrolled fashion. Okay, so number 2 will be react these enols or enolates with less reactive acylating agents. Example, esters. Okay, so let's take a look at some specific examples using esters, also known as the Kliesen ester condensation. This didn't do such a good job erasing. I'm just going to get my spray bottle. To clean this up. In fact, when I come here every couple days or every few days, and they're supposed to clean this room, but they don't really clean the boards. They just wipe it down, but there's this gray residue on here. So this should help. I hope. Look at that. All right, so let's look at the Kliesen ester condensation of acetates. Okay, so here's an ester, and if we want this group to react with a molecule of itself, So like a self-condensation, you can imagine we want to create an enolate, and then we want to react with itself, which is a mild acylating partner. What would be the best base to use for this ester? You could use LDA for sure, but LDA, you got to control it, use it at low temperatures. There's a much simpler base we could use. We could use the alkoxide base of this leaving group here. So we could use sodium, for example, sodium ethoxide in ethanol. And the reason, again, just to remember why we use this and why it's okay, is because the ethoxide, if it reacts with this ester, it's the same group coming off. So nothing productive comes out of that. So it's a great base to use. So when it acts as a base, it's going to pick up this alpha proton, and it's going to generate the enolate. And then when this enolate comes and reacts with itself, electrons will come down, carbon-carbon bond, you'll generate an intermediate like this. That's your new carbon-carbon bond right here. And then this will come down, displace off your ethoxide group, which is also your base. So that's good. And what you're going to generate is you'll generate this compound as I'm showing you here. Now in terms of a mechanism, when we do this first step, recall that the pK of the conjugate acid of alcohols is around 15 to 16. The pKa of these protons here are around 21 to 22. So in terms of this being an irreversible base, it's not. It's an actual reversible base, meaning that these steps here are all reversible. Once this comes and reacts, the reverse could happen too. So all these steps are reversible. So the question I have for you is that we are in the solution with a base whose conjugate acid is around 15. Mechanistically, is that going to be the final product? And remember, we have an alpha proton here that's between two carbonyl groups. Recall that the pKa of protons that are between two carbonyl groups significantly lowers, roughly between 11 and 12. So now we have a very acidic proton, much more acidic, and we have ethoxide. So ethoxide, whose conjugate acid has a pK of 16, sees this proton, which has a pK of around 13, it's going to immediately pick up that proton and delocalize it on one of the sides of the carbonyl. When it does that, this step is going to be irreversible. This is an irreversible step because the pK of this ethoxide that you generate is around 15 to 16. Recall our discussion that we had on the first lecture about the importance of pKa and how the equilibrium always lies on the side with the weaker acid and weaker base. So you can see here that the weaker acid is here, 16, compared to 13. So this is the irreversible step. And this delocalized carbanion or enolate like this will stay in solution until you do your workup step. So in terms of how this works, I'm just going to move the ethanol up here. And we'll call this step 1. And then step 2, you're going to have a workup step. And your workup step will be, simply water, maybe a little bit of acid. And what that's going to do is during step 2, the workup step, that's going to allow you to pick up a proton to generate the product. So there's your product. Note that this is the same structure as I'm showing you here, but in terms of how we do this mechanistically, you have to go through that irreversible step because we've generated a much more acidic proton. Okay. So again, all steps are reversible except for that irreversible step. Good stuff. Let's look at one more example before we end this lecture. I think I would prefer to use the chalkboard, so just bear with me. So we're going to go through a very similar example, and this is going to involve this compound here, and the question is going to be same. Let's do that let's do that self-condensation of this ester. So you can say, okay, very good, I just learned a great lesson here on this condensation of esters to generate this Kliesen product. Let's use the same base here. Okay, so you have an acidic proton here. Your ethoxide will come. You do that, you're going to generate your enolate, right? And then this is going to react with another molecule of itself. And I won't go through all those mechanistic steps. You can see that once this comes and reacts, then your tetrahedral intermediate will come back down. Okay, so this is going to look like well, you know what? Maybe I'll just go through all the steps just to make it consistent. Right? I want to make sure if I'm asking you for a mechanism that you show me all the steps. So let's not rush it. Okay, so you form this intermediate here, and then you can see here that your tetrahedral intermediate will collapse. You'll kick off the ethoxide, and you will generate this compound here. Okay? And you go through, and let's say you set this up, and you know that these are all reversible because you understand pKa. And then you come back a few hours later or the next day, and you try to isolate the product, but you notice that you get very, very low yield. And in fact, most of your product is just unreacted starting material. And you're wondering why that is. And you do this over 2 steps, of course. You do the workup step. and your product still remains in low yield. All right, so how can we fix that, and why is that the case? The reason it's in low yield is because you don't have the protonation when you make these two carbonyl groups through a central alpha carbon. Okay, so recall over here, you have this highly acidic proton around pK13, and you have this irreversible reaction that really drives that reaction forward. In this case here, you don't have that. There are no acidic protons here, so there's nothing driving this reaction. Everything's in equilibrium. Okay, so that's why you get the low yield. How can we solve that problem? What if this actually is what you need to make, and you need to make that in high yield? How could you do that? I'll just write, because we can't push the reaction with a final irreversible step. So how could you make that in high yield? And think of irreversible step. You need to use and have an irreversible step somewhere. Well, what is a good base that is strong and sterically hindered that will give you an enolate irreversibly from step one? So instead of using ethoxide, let's use LDA. LDA has a conjugate acid whose pKa is around 36. So that's really quite high, whereas the pK of this is around 21 or 22. So if you treat this with LDA, then this first step is going to be irreversible, and you're going to generate this enolate, and then in step two, in a controlled fashion, you add your ester, which is the same molecule that you want it to react with. And this will react, because this first step is irreversible. When you form this complex up here, it's going to be formed in high yield. Okay, so the choice of base can greatly influence the yield and the outcome of the reaction. Okay, so that is your first lecture on acylation at carbon and looking at Kliesen ester condensation. All right, stay tuned soon for lecture 21, which will look at cross ester condensations. See you then.